Hey, welcome to Klein's Calculus. We're going to look at continuity, lesson 2-3 today. And again, there's always some more videos on the details on the Moodle. Thinking about things that are continuous, life, time, things that don't break or end, a path. Lake Michigan Drive is continuous till it gets to the lake, then we see a bit of a break. When you think about calculus, most of the techniques that we require, looking at derivatives, looking at integrals, they require a function to be continuous. And continuous means, quite simply, you can draw it in one motion without picking up your pencil. Okay? So when you and we don't throw out all the functions that isn't possible with. What we say is, okay, if it's continuous in this particular area on this interval, then we can still find a derivative, find an integral over an area, that sort of thing. So we just look at it over a period. So a function is continuous at a point if the limit's the same as the value of the function. There's no hole, there's no asymptote. And we look at function intervals, domains for continuity. It doesn't have to be continuous over all the real numbers. Now, if you look at this function right here, it has discontinuities at x equals 1. You see the jump. We've seen this function before. Because it has a jump. You know, here it is, and then wham, all of a sudden here it is. And it has a hole here at 2. But we can also say the function is continuous from 0 to 1, from 1 to 2, and from 2 to 4. So it is discontinuous at x equals 1 and x equals 2, but it's continuous throughout the rest of these intervals. So it's continuous at x equals 0, and it's continuous at x equals 4, because even though it doesn't go any further, this is the end of the domain, and the function has a value at x equals 4, and it has a value at x equals 0. So if the domain is from 0 to 4, and it's going where you expected it to go, the limit is the same as the value of the function, the left-handed limit here and the right-handed limit here, then we still say it's continuous there. It's just discontinuous at 1 and 2. Now there's a couple kinds of discontinuities. There's a removable discontinuity, because if that was a value of 2, I could just make a piecewise function and say, hey, right there, x equals 2. Fill in the hole, you're all set. Here, I could say, hey, x doesn't equal this anymore. X equals 2, or whatever that is. Fill in the hole, and it's a removable discontinuity. Looks like a problem, but we can fix that. Some discontinuities you can't fix. Jumps like this, not fixable. Think about your step function, your absolute, or excuse me, your not absolute value function. The step function. I'll come to it later. Think about the infinite function, those rational functions like we just looked at in lesson 2-2, where you have like 1 over x squared. And then think of things like sine of x over x, where we're oscillating and we're just crazy everywhere. And then it has a jump right in the middle. So how do we remove a discontinuity? Let's say we've got this function, f of x equals x cubed minus 1 and x squared minus 1 over x squared minus 1. And we know at 1, this would equal 0, so there's a hole in the graph. So we just write an extended function, and we define it at x equals 1. So if we were going to find out what it should equal at x equals 1, we can take the limit as x approaches 1 of x cubed minus 1 over x squared minus 1, and factor to figure it out. I've got x plus 1 times x minus 1. That's the difference of 2 squares. And then I'm going to look at this and say one of these needs to be a factor of this. Because of that negative sign, I'm guessing it's that one. Do a little division, synthetic or polynomial, don't care, and you'll find this is the other part of it. So if you divide x cubed minus 1 by x minus 1, you'll get this. Those will cancel out. Now I can put in a 1. And I'll get 1 plus 1 plus 1. I'll get 3 halves. So that's what the function intends to do at x equals 1. But there's a hole. So I can write out this nice piecewise function where I say f of x equals x cubed minus 1 over x squared minus 1. That's my original function. If x does not equal 1, because that's where the discontinuity is, and f of x equals 3/2 where x does equal 1, because we figured that out. So that's how you remove your discontinuity. And if you go with this, you've got a continuous function. You're in good shape. So, however, yeah, do keep in mind, it's continuous at x equals 1, but there's still a discontinuity at x equals -1. Recall that anytime the denominator equals 0, you have a vertical asymptote where x plus 1 equals 0, x equals -1. So there's going to be a discontinuity there, and we can't get rid of that because x plus 1 is not a factor of this. So sometimes you can fix them, some you can't. Do what you can. So continuous functions, the nice thing about continuous functions is once they're continuous, you can add the functions, subtract them, multiply them, divide them, multiply by a constant. You can do all of the things you could do with just numbers, and the new function will stay continuous. So if I'm combining a couple continuous functions, the only thing I can't do is I can't divide by the other function if it's going to equal 0. And composites of continuous functions will be continuous also. So if I have sine of x squared, continuous function. Absolute value of cosine of x, continuous function. Or excuse me, sine of x squared, that's continuous because x squared is continuous and the sine of x is. Cosine of x, absolute value of that, the absolute value function is a continuous function. Cosine of x is a continuous function. Therefore, this is a continuous function also. So the intermediate value theorem, which is a wonderful video in and of itself on the calculus phobe, please make sure you take a look at that, says if a function is continuous between a and b, it takes on every value between f of a and f of b. Here's what that means. Here's our function, it's continuous from here, and f of a is right here, and f of b is right here. So we know for sure if this is continuous and it starts here, no matter what I do with my pencil to get from here to here, I've got to get every y value along that line. If I don't pick up my pencil, I hit them all. So that's your intermediate value theorem. We're going to use that quite a bit. That's kind of one of those hot topics on the AP test. So make sure you watch the calculus phobe video and we'll do some stuff for that too. So it's got to take on every value, every y value from here to here. It doesn't, this is bonus stuff. But the intermediate value theorem guarantees everything from there to there. So, and here's one way we might use it. Is any real number exactly 1 less than its cube? It doesn't say what real number. It just says, is any real number. So we just want to know if it exists. So that means, is a real number equal to exactly 1 less than that number's cubed? So we could write this statement. And if I was going to solve something like that, I just set it equal to 0, and now I've got this equation, this function. And then my question would be, it's just a function, does that have, can I solve this? Does it have a 0? If it has a 0, then that would be my answer. We don't need to know where it is. Well, I know f of 1 here is going to be 1 minus 1 minus 1. Oh, excuse me, f of 1, no, f of 1 here, 1 minus 1 minus 2, so -1, okay. And if I look at 2, just putting some numbers in to play with a little bit, I get 8, minus 2 is 6, minus 1 is 5. Now, if f of 1 is -1, so here's 1, here's 2, and f of 2 is 5, then somewhere by the intermediate value theorem, it took on the value of 0. That's all you need to do. Just try a couple numbers once you've got a function. We don't even need this, we just need that. But if we graph this, we can see, calc intersect, you can see if there's a 0. Since f is a continuous function, you can just say by the intermediate value theorem, it takes on every value between -1 and 5. So there's got to be at least one solution between 1 and 2. We don't need to know what it is because it doesn't ask that. And we gave an idea where it was, so that's good. We can graph this, calc 0, and get an approximate solution. Little commercial reminder on that, whenever we're doing AP Calculus, we round to at least 3 decimal places beyond, or 3 places beyond the decimal. So at least the thousandths place. You can go more accurate, don't ever be less. Or, so we could do this calc 0, or we could put this in the y equals x, and this in the y equals x squared minus 1, and we can calc the intercept. That will get us there also. However you do it, y1, y2, calc intersect, or all this together, calc 0, you should get 1.32472, at least 1.325. Now, just be aware, your graphing calculator will make non-continuous functions look continuous. You got to be real careful. Graph y equals floor of x, and it takes your step function, absolute value, and it connects them. And this isn't really part of the function, but it's what you're going to, or not absolute value. I don't know why I'm forgetting that one, but I will get it by the end, I promise you. It will connect the dots as you go up, though. Integer, greatest integer function. Thanks, sorry. So if you did, in our calculators, it's y integer x. And it should look like that. And some calculators are just going to fill in these discontinuities. You're going to look and go, it's a continuous function, but it's not. So check that sort of thing. Look on your table, see what's going on. Okay? And you can change the plot style to dot instead of continuous, and the resolution to 1, and then you're going to start seeing it. Then you can see the discontinuities, and that's what you want to have on your graph, so don't let it fool you. Okay, and that is the end of continuous functions. So if you can pick up your pencil, it's not continuous.